So thank you. First of all, some of you probably noticed that I changed my talk. I changed the title of my talk and the content of my talk. The reason is that I saw that there would be someone talking about black hole thermodynamics, but no one talking about statistical mechanics outside of physics. So I thought I wanted to fill that gap. And I changed the talk, so I'm going to talk about exactly that. So in 1940, oh, sorry, this doesn't. In 1944, Schrödinger published this book that is called What is Life, in which he tried to explore the idea of applying statistical mechanics and thermodynamics to biology. And in particular, what he wanted to do was to see to what extent one could use statistical mechanics and quantum mechanics to explain the origin of life. And at the very beginning of that book, he says, a scientist is supposed to have a complete and thorough knowledge at first hand of some subjects, and therefore is usually expected not to write on any topic of which he is not a master. This is regarded as a matter of noblesse oblige. For the present purpose, I beg to renounce the noblesse, if any, and to be freed of the ensuing obligation. So he used that to apologize for talking about things that he wasn't an expert of, like biology. And I use the same quote to apologize for talking about so many things in which I am not a very expert. But you will see why. So before we move on to the interesting things and the possible applications of statistical mechanics everywhere, let me just give you a very short summary of how statistical mechanics works for the so-called classical domain or the most traditional domain. So as many of you know, especially here in this audience, statistical mechanics was developed from the middle of the 19th century, right? And it was originally a theory of ideal gases, which are sort of well-behaved. So in a nutshell, if we consider a gas that is in half of a container, and we imagine that the gas is separated from the rest of the container by a wall, and then we imagine that we get rid of that wall, then we will see that the ideal gas will expand, right? And then we can also have some nice properties here. So we know that the particles will travel at a typical velocity, v, and will collide with each other after traveling a typical distance, L, that is called the mean free path. The interactions here are supposed to be short range, right? So, which means we are neglecting the effect of long range forces like gravity or the Coulomb force. Also, the evolution of the distribution function is described by the Boltzmann equation. We will hear more details about the Boltzmann equation tomorrow. And another property is that independently on the initial conditions, we know that the system will evolve towards an approximate Maxwell-Boltzmann distribution. Now, another aspect that is important in this picture is that the relaxation time, that is the time that that the system needs to equilibrate, is going to be proportional to this mean free path over the typical velocity. And it's not going to be proportional to the number of particles, which means that a very big system and a very small system will equilibrate at the same rate. Now, a little bit after the 19th century, so after Boltzmann's contributions, statistical mechanics was applied to magnets. And in order to understand magnetization and phase transitions within ferromagnets, scientists propose different idealized models that are commonly used to understand the behavior of ferromagnets, for instance. And the most important model that is an idealized model was proposed exactly 100 years ago. That is the Ising model proposed in the 1925, which is a lattice model in which we assume that the particles are represented by points in this lattice and that they can only have 2 degrees of freedom. That means up or down. So in 2 dimensions or higher dimensions, the Ising model exhibits a phase transition from paramagnetic state at higher temperatures in which the spins are randomized to a ferromagnetic state, which means that there is some spontaneous magnetization. And this happens, as I said, at a particular critical temperature. So this model, like the Ising model, is associated to a particular Hamiltonian that is here, in which this J here is the coupling constant that determines the interaction here between the particles, and this H here is an external field. Right? There are other idealized models that are used to explain, to understand the behavior of ferromagnets, like the Heisenberg model, the X-Y model, etc. The Botz model as well. But now this was 1925 and beyond. But now, especially in the last 50 years, statistical mechanics has been applied to very different domains. One example is the application of statistical mechanics and thermodynamics to self-gravitating systems, which are systems in which the effects of gravity cannot be neglected. Or another definition is that they are systems that keep together because of gravity. So examples of self-gravitating systems are clusters of stars, galaxies, and what scientists have been doing lately is try to apply not only thermodynamics, but also statistical mechanics to this type of systems. The motivation is that in these systems, we find some properties that remain constant in time, like the luminosity profile, for instance, the density, the number of particles, and also that one can find some particular distributions, probably statistical distributions that resemble typical distributions, like the Poisson distributions. Another example of the extension of statistical mechanics and thermodynamics to different domains is the so-called black hole thermodynamics. So this was also developed in the last 50 years, starting by this seminal paper by Bekenstein, in which he proposed that black holes have associated a certain entropy that was called the black hole entropy that was proportional to the surface area here. So by that assumption, he also generalized the second law, proposing that the total entropy is equal to the black hole entropy plus the normal entropy, and that total entropy cannot decrease, right? So I'm going to tell more details about this later. But the use of statistical mechanics and thermodynamics have gone beyond that. And we can find that also now, especially in the last 30 years, statistical mechanics have also been used in the context of biology, not only population biology, but also molecular biology and different areas, the study of cancer, etc. A successful application of statistical mechanics is to study flocking behavior, which is these beautiful patterns that we see when birds flock in the sky. So in order to understand this behavior, scientists have taken inspiration from models that were used for ferromagnetism, like the Ising model, and they have proposed new models like the Vixek model that are quite successful. So these models help us not only explain what could be the basic mechanisms of flocking, but also help us predict the instantaneous positions of birds in a certain time, which is quite remarkable. So by using statistical mechanics, one can also explain flocking behavior as a transition from a disordered phase to an ordered phase. And the same, without giving so much details at this time, happens with financial markets. So statistical mechanics have also been applied lately to study financial markets, and in particular to explain why market crashes. Although this has been less successful than the case of flocking behavior, there has been important progress in which idealized models of financial markets at least give us a very rough qualitative explanation of why markets might crash. More recently, in the last 10 years, there have been also applications of statistical mechanics to analyze the phenomenon of opinion polarization and echo chambers, which are very relevant phenomenon right now. And I would confidently say that scientists are reaching some results, some interesting results in this field. So I will also tell you, perhaps if I have the time, more details on this later. But all of this raises very interesting questions that have been not explored much in the philosophy of statistical mechanics. The first is, what justifies the export of statistical mechanics to all these foreign domains? Although there has been work by philosophers on the use of statistical mechanics to these domains in isolation, there has been no work in which we compare actually the use of statistical mechanics in across domains, in all these domains. The second question is, what elements of statistical mechanics can actually cross domains? The third question, are these systems governed by thermodynamic principles, or is it just a formal analogy what is going on here? And finally, is there a unique answer to the previous questions, or is this domain dependent? So what I'm going to do today is to start answering these questions. I'm not going to give the answer to all of this because this is a very long research project in which I plan to work on in the next years, but I will start telling you what my thoughts are on this comparison. So this is the plan. First, in order to understand or to answer these questions, we need to go a little bit through the literature on knowledge transfer, which has been developed mostly not only in the literature in philosophy of physics, but in general philosophy of science. So one might think that the motivation to use statistical mechanics to many different domains, from black holes to stock market crashes and opinion polarization, has to do with something like the law of large numbers. So this is what Schrödinger himself called the naive physicist approach, which is the idea that because there are many particles or many individuals or many molecules in the process, we find roughly the same statistical distribution. So this basically justifies us to use the same framework like statistical mechanics to analyze different types of domains. So this is what Schrödinger, as I said, called the naive physicist approach, and is the approach that he criticized, especially by considering biological processes. A second approach that is very similar to the naive physicist approach is what I call the universality approach. So this basically says that what justifies us to use statistical mechanics to understand different types of systems is that the phenomena at stake are universal, in the sense that they don't care so much about the details, but basically it is the same behavior, the same macro behavior that is instantiated in different types of systems. So this gives us reason or a justification to use approximately the same framework, at least macroscopically, to different type of systems. So some philosophers that have been putting forward this framework in different contexts are Battelman and Rice in these papers, but this view can also be found and defended by has been defended by some physicists, for instance, Unruh and Schutzhold, in the context of black hole physics, who have appealed to universality to justify the use of analog experiments in that context. So the idea here is that the macro behavior at stake is universal in the sense that it can be instantiated in diverse physical, biological, and socioeconomic systems, and that appealing to universality enable us to use the same idealized models to explain behaviors of different systems, despite differences at the microscopic level. This idea of universality and also the physicist, the naive physicist approach, gives also a justification to have an imperialist attitude in the transfer from statistical mechanics to other fields, which is basically the idea that we just extend or expand the domain of statistical mechanics to cover other domains. So the imperialistic approach can be defined as follows. So it happens when the domain of validity of a model in one discipline expands to include other target systems previously described by different disciplines, and it is based on the pursuit of ontological unification. So what happens with when we try to use or expand statistical mechanics to other domains in an imperialistic way is that we try to find unification between different domains. So there's not so much room for modification or for reinterpretation of the variables, etc. Another attitude, another type of approach is the template approach, which is different from the imperialistic approach in the sense that it's not, the transfer is not just an extension of a certain discipline or a certain model to a new domain, but basically what happens here is that we transfer certain elements from one model or from one theory to the other. And the elements here are called the template, which basically consists on the mathematical structure and a generic conceptualization. So here it is not the whole theory or the whole model that is applied from or is extended from one domain to the other, but it is a template of that model or the theory that is used in different domains. And as I said, the template normally is defined as the mathematical structure or the generic conceptualization of the model. There's also the analogy or the migratory approach. So the analogy approach just focuses on the analogy, on the analogical aspects of the original domain and the target domain. And there is another type of approach that is called model migration, which is different from imperialism in the sense that we transfer one model from one discipline to the other, and not just by extending the domain of that model, but just by reinterpreting the idealizations and the ontology according to the new domain. So here is the schema for model migration that Bradley and Thibault proposed. But what I want to put forward here is a different approach to knowledge transfer that I think applies for most of the cases of the export of statistical mechanics to other domains, which is what I call the adaptive approach. So the adaptive approach can be defined as follows. A model can be transferred from one domain to another if there is enough adaptation, which means that the new model or the new theory integrates certain universal, causal, and formal properties that come from the original domain, but also integrates certain domain-dependent properties, some of which have with no analog in the original domain. So the idea of adaptation is that we distinguish it from the imperialistic approach in the sense that adaptation requires the incorporation of new properties that have no analog in the original domain. And there is finally a different attitude that we can take in the export of one discipline or some elements from one discipline to the other, that is the skeptic approach, which basically tells us that because important these analogies between the classical or the typical domain of thermodynamics and the new domains, we should just be skeptical about the use or about the extension of statistical mechanics to new fields. And this is very nicely represented by this in this quotation by Rawlinson. So he said thermodynamics is essentially a human science. It started with steam engines and went on to describe many physical and chemical systems whose size is of the order of a meter. Its laws are not truly a theory, but a highly condensed and abstract summary of our experience of how such systems behave. We have therefore no right to expect them to apply to other quite different systems, whether extremely large or extremely small. They clearly are inapplicable to solar systems or to galaxies. So this is the idea that we should just stop trying to apply statistical mechanics everywhere, and we should just give a step back and recognize certain crucial disanalogies between the typical domain, statistical mechanics, and the new domain. As I said, what I will try to do is to put forward the previous approach that I call the adaptive approach. So now let us examine some important cases of transfer of statistical mechanics to other domains. And I will start by discussing certain examples of intradisciplinary transfer. This is when we go from physics, from some areas of physics to other areas of physics. So the first example that I mentioned before was the application of statistical mechanics and thermodynamics to long-range interacting systems. So when we try to apply statistical mechanics to long-range interacting systems, the first disanalogy that we find, it has to do with gravity. So normally, as I said at the beginning of the talk, when we consider typical systems in statistical mechanics, we assume that interactions are short range. But what happens when we consider long-range interacting systems is that we have to take gravity into account, which is a long-range force. The action of gravity leads to different disanalogies with respect to these systems and the typical systems studied by thermodynamics. For instance, if we include gravity, we came up to the effect that we can find negative specific heat in the microcanonical ensemble. We will find an inequivalence of the canonical and microcanonical ensembles. We will find breaking of ergodicity in microcanonical dynamics. And finally, there will be a disanalogy with respect to the relaxation time. So as I said at the beginning, in the case of short-range interacting systems, relaxation time is not proportional to the number of particles, but in the case of long-range interacting systems, relaxation time becomes proportional to the number of particles, which means that we will have problems when we use the thermodynamic limit, because it will mean that the system will never equilibrate, right? So all these analogies had several consequences, but there was still, at the beginning of the 70s, an attempt to use the same statistical mechanics that was used for short-range interacting systems to long-range interacting systems. And it was proved that one could use a collisional evolution governed by the Fokker-Planck-Landau equation that for which there was an H theorem available, so an H theorem that maximizes the entropy. But despite certain success in these approaches, they found an important problem that was called the fundamental paradox of stellar dynamics. And it's that if we use the collisional evolution equation, because of this analogy with respect to the relaxation time, we will arrive at the conclusion that the systems, like clusters of stars, for instance, equilibrate in a time that is 10, for instance, 10 to the 8 years, the time of the galaxy. So this led to a very important foundational program. And they forced some scientists or physicists working on this approach to replace the approach and to replace the evolution equation by the collisionless Boltzmann equation that is also called the Blasov equation that was originally used to study plasma. So by using that, they derive a relaxation time that wasn't dependent on the number of particles, so they solved that paradox of stellar dynamics. But they found other problems as well, and it's that the equilibrium states that are associated with the Blasov equation not all maximize the entropy, which basically led to the new problem of having to decide which equilibria states were physically plausible and which ones were not physically plausible. So Shabani, for instance, discusses these issues. The important message here to take home is that there are several problems with the imperialistic attitude, which is this idea that we can just extend the scope of statistical mechanics to this new domain, like self-gravitating systems. The first problem that one finds is that because of the problem of the relaxation time and similar problems, we have to admit or conclude that perhaps the mechanisms that underlie the equilibration of self-gravitating systems are different from the mechanisms that underlie the equilibration of ideal gases. For instance, in gases and magnets, the relaxation is driven by neighboring interactions, whereas in stars, for instance, the relaxation is most likely, this hasn't been decided yet, but most likely driven by fluctuations in the mean field, which is the approach by Lindenbelt. Of course, there is another important disanalogy concerning the ontology. In the case of magnets and gases, we have particles. In the case of self-gravitating systems, we have stars, right? But there is also a different conception of equilibrium. If we use the collisionless evolution, then we will have to understand equilibrium not in terms of stationary states, but in terms of metastable states, which will again lead to important differences in the way we understand and define thermodynamics for self-gravitating systems versus thermodynamics and statistical mechanics for gases and magnets. So what is happening here is that the more the field advances, the more we see certain adaptation of the tools and the framework of statistical mechanics to this new domain. For instance, although the Blasov equation helps us understand conceptually the notion of equilibrium for self-gravitating systems, different notions of entropy have been proposed to choose between physically plausible equilibrium states. And there have been definitions of entropy that have been proposed as sui generis to self-gravitating systems, like Sally's entropy, for instance, and Lindenbelt. Now, the second case is black hole thermodynamics, and I will try to describe more briefly. So another field that has been very important and developing in the last 50 years is the use and the application of statistical mechanics and thermodynamics to black holes. And what has motivated this study are very important, striking analogies between the laws of thermodynamics and the laws of black holes, and in particular, stationary black holes. For instance, there is an analogy with the zero law, in which in thermodynamics we take T to be constant on a body in thermal equilibrium, whereas in black holes we take the surface gravity to be a constant in the horizon of the black hole. There is also an important formal analogy with respect to the first law that you see there. There is an analogy with respect to the second law. So in the second law, we say that entropy cannot decrease in black hole thermodynamics. It's the area, the surface area, that cannot decrease. And there is also an analogy with the third law of thermodynamics. So according to some physicists, these analogies suggest that black holes are thermal, and that we can actually apply the laws of thermodynamics to this type of systems. So an important attitude that has been defended in this literature is very similar or very close to the imperialistic attitude. For instance, Wald in 1994 says the results described in the previous sections provide a remarkably compelling case that stationary black holes are localized thermal equilibrium states of the quantum gravitational field, and that the laws of black hole thermodynamics are simply the ordinary laws of thermodynamics applied to a system containing a black hole. So this is very similar to what we would call an imperialistic attitude. There is no really, he's not trying to mark a difference between black thermodynamics as applied to black holes and thermodynamics of gases or magnets. So basically what this suggests is that what causes your T to come to room temperature is said also to cause the area of black holes to increase. Now, philosophers of science and also physicists have shown some problems with this imperialistic attitude. Actually, one of the problems were actually emphasized by Wald himself in the same paper. So he said, although there are many reasons to consider black holes as thermal, there are some problems that need to be solved, for instance, about some paradoxes that appear when we try to apply statistical mechanics and thermodynamics to black holes. So one important paradox is the information loss paradox. But another important problem is that it's not clear, although there are different proposals now, at least originally, it wasn't clear what entropy really meant for black hole thermodynamics. So it wasn't clear what were the degrees of freedom responsible for black hole entropy. Another problem that was suggested by Dougherty and Callender in this paper of 2016 is that black hole thermodynamics is based on a caricature of thermodynamics. So basically they said in the paper that the analogy between thermodynamics and black holes was just a very weak formal analogy, nothing more than that. So they were very skeptical about the application of thermodynamics to black holes. Another disanalogy or problem is that it's unclear what black hole thermodynamics, the systems in black hole thermodynamics are supposed to be. That's also a critique posed by Dougherty and Callender. They said that while ordinary thermodynamical systems are local systems that exist in some region of space-time, classical black holes are not. And finally, there is also another problem posed by Eugene recently. He says that black hole thermodynamics needs to apply to relativistic regimes, which is true, and what he shows in that paper is that it's not, if we think about the concept of temperature, then we will see that it's not that trivial to apply relativistic effects to classical temperature. So now we can zoom up on these analogies and see some problems or potential problems with all the laws, the apparent laws or the suggested laws of black hole thermodynamics. So again, Dougherty and Callender said that there are problems with the zero law of black hole thermodynamics, because in black hole thermodynamics, there is no equilibrium width relation. It's very hard to understand what equilibrium width means. There is a problem with the first law as well, because there is lack of a local notion of energy in general relativity. There is a problem in principle, also with the second law, which was posed by Wald himself when he explained his skepticism with this discipline when he started learning about it. So he said that he was very suspicious about this, about marrying the area theorem proposed by Hawking with the second law, because the area theorem is a theorem of differential geometry, whereas the second law had a statistical origin. And finally, there is another problem that was also posed in this paper by Dougherty and Callender that has to do with intensive and extensive quantities. So they said that whereas entropy and internal energy are famously extensive, that means that they scale with the system size. Temperature, by contrast, is intensive. But what we find in black hole thermodynamics is something very different. For instance, we find that entropy and internal energy are not extensive. And we also find that temperature varies inversely with the system size. So there are a lot of disanalogies between them. So basically what they conclude on the basis of all of this was that we should be very skeptic about the use of thermodynamics to black holes. So they say what we are arguing is that the analogy might not be more than formal. First, we have shown that the analogy is not that tight. Similarity is in the eye of the beholder, yet one only sees similarity between the two theories if one very selectively focuses on some parts while ignoring others. And then he said something that I will also contest a little bit. He says, black hole thermodynamics might go in the way of thermoeconomics, as if that would be a bad thing, right? That is why we recommend hedging one's bets, right? Good. So there is some reply to this by David in two papers. Actually, here I got the thermodynamics paper, but there is a sequel paper on black hole statistical mechanics. He says that black hole thermodynamics is not a caricature of thermodynamics, but thermodynamics of extensive systems. If we focus instead on certain types of self-gravitating systems, then we will see that this analogy doesn't hold that much. In fact, and you correct me if I'm wrong here, but in fact, black hole thermodynamics as self-gravitating systems are non-extensive, and that's fine. For instance, if we think about dense spheres of radius approximately 5 Schwarzschild radius, then we will see that gravitational effects become highly important and that the system displays several distinctive features characteristic of self-gravitating systems. Similarity with self-gravitating system is non-extensivity, non-additivity, and negative heat capacity. So, and then he also contested different arguments given by Dougherty and Callender in an appendix, which I found kind of a very nice strategy as well, but also within the text. I'm not going to go through all of that because I am giving enough details already. But I am going to propose something a little bit different. So it is true that if we think about certain type of self-gravitating systems, then we see a lot of analogies between black hole thermodynamics and these self-gravitating systems. For instance, dense spheres. But if we consider other self-gravitating systems, for instance, clusters of stars or galaxies, then we will again find some disanalogies that are not decisive to take a skeptical attitude about black hole thermodynamics, but that make us maybe a little bit more cautious about this apparent analogy between the two domains. For instance, all the work by Lindenbell and Salis suggest, and the idea of what is called violent relaxation in self-gravitating systems, suggests that we should take equilibrium, or we should interpret equilibrium of self-gravitating systems like galaxies or clusters of stars in terms of metastable equilibrium, which means that the system will stay there for a long time until it moves on to another state that might ultimately correspond to the Maxwell-Boltzmann equilibrium. Now, the difference with respect to black holes is that there are different types of black holes. So we have stationary black holes, and we have also some metastable black holes. So some type of black holes might correspond to equilibrium or might be closer to how we understand equilibrium for self-gravitating systems. But some other black holes might be actually might behave actually more nicely than self-gravitating systems. There is another, this is more obvious, this analogy at the microscopic level, right? Of course, one of the big questions, which again, I don't think is a decisive argument against black hole thermodynamics, but one of the decisive questions is, what are the degrees of freedom that constitute entropy or that lead to entropy in black hole thermodynamics? This is a big question. There are a lot of theories that are very interesting, but in the case of certain self-gravitating systems like galaxies, this is quite clear. We know what we are talking about. We are talking about stars, or we are talking about macroscopic objects that, in a way, are more observable than gases. Whereas in black hole thermodynamics, this is a big question. We have no access to these degrees of freedom. Now, there is some work in physics that has pushed this analogy between self-gravitating systems and black holes a little bit farther. And actually, some physicists like Wong Jung are working on certain approaches of entropy of black holes that relies on Sally's entropy, which was precisely defined for long-range interacting systems like self-gravitating systems. So there is work in this direction. But this is just one proposal of entropy of many that have been suggested in the last years. And you can see a review of different possibilities for black hole entropy in this very nice paper by Alan Harris. But I will not say much on that. There's a lot of work that could be done in this direction of to what extent are black hole thermodynamics analogous to self-gravitating systems. But this is just like the preliminary ideas that I have in this direction. So what I see in this literature is that there are two dominant positions. One is what relies on the universality of certain properties that might be instantiated in black holes and also other systems studied by thermodynamics, and also associated to the imperialistic approach in which we say that black holes are thermodynamic systems in the fullest sense of the term. And there is another dominant position, which is more skepticism. So it's based, they assume that the motivation to develop black hole thermodynamics is only based on a very weak analogy between black holes and the system studied by by thermodynamics, which leads to a very skeptical attitude about the entire project. So what I'm going to propose are as an idea, right? I want to work on this in the future. It's an intermediate position, which I think will be helpful for other applications of statistical mechanics as well. So I call this intermediate position adaptation only because I stress here the importance of adapting the laws of thermodynamics to the specific intended domain, in this case, black holes. So there are important disanalogies between the classical domain of thermodynamics and black hole. Important disanalogies between the classical domain of thermodynamics and black hole thermodynamics led to an important modification of the thermodynamic laws and a sui generis definition of key terms of thermodynamics, like temperature and entropy, that are defined differently in black holes than in other domains. But, and here I will fully agree with the papers that David wrote, the development of black hole thermodynamics, especially in the last 20 years, is suggesting a more deeper connection between the typical thermodynamic systems and black hole thermodynamics, which might also suggest that there are some similar causal properties also in the two different domains. So I would say adaptation is something that would admit these two different observations. It will emphasize, on the one hand, the disanalogies between the classical domain or the typical domain and the new domain. But on the other hand, it will allow for a more deeper connection than just a formal analogy. But there are still key questions that I would like to answer. I don't have, if you have the answer to this now, you can tell me so I save time. But one is which exactly are the causal and formal properties that are transferred from the classical domain to black hole physics? Which properties are domain specific in contrast to apply to all long-range interacting systems? What is the difference in the transfer of statistical mechanics to black holes versus other self-gravitating systems, which is something that is still not clear to me? And finally, there is something related with the idea of universality classes. So I would like to understand whether we can distinguish between different types of universality classes in black hole physics, some of these classes which are more susceptible of the laws of thermodynamics than others. So there are different types of black holes. We know that there are some black holes that are more nicely behaved than others. So I would like to understand whether this makes sense to separate them between universality classes, some of which might be, as I said before, more susceptible of the use of thermodynamics. So let me now move to the last step. Now, Callendar and Dougherty said, as if it would be a bad thing, that they don't want black hole thermodynamics to have the same destiny as socioeconomics, as if it would be insane to use statistical mechanics to economics. I will contest that, and this is more my confidence on. Something that is only rarely recognized when we think about the application of statistical mechanics beyond the classical or the typical domain is that in some cases, this is very successful. And when I think about success here, I'm thinking about empirical success. Of course, it's hard to talk about empirical success in the context of black hole thermodynamics, but it's easy to talk about empirical success in the context of flux. So in 1995, Bixek developed a model, a very idealized model for flocking behavior that relied on statistical mechanics, on very idealized assumptions from statistical mechanics, and that was motivated by an analogy with the Ising model. The model was very idealized, but with a bit of calibration, has actually produced very, very interesting results. One can use these very idealized models to run simulations of more than millions of birds and see accurate results, but also these models have been contrasted by empirical data. Actually, they have predicted approximately the instantaneous positions of three-dimensional data of real flux, which is a project that is called the Star Flag in Rome. This is very interesting because, as in the case of black hole thermodynamics, we find many disanalogies between biological systems and the physical systems. Biological processes occur out of equilibrium. Biological systems normally have fewer symmetries than typical physical systems. And biological systems are active. For instance, flux are active. They decide, they put themselves in motion. And usually they are much more complex than the typical physical system. So then the question is, how possibly could we use statistical mechanics here? But they do. So they built a new model, which is, as you know very well, inspired by the Ising model, but very different from the Ising model at the same time. So first of all, they propose, even if they were inspired by the Ising model, they propose an off-lattice model. So here we don't represent birds sitting represented by points in a lattice anymore. They changed the Hamiltonian, and now we are not thinking about, energy alone, but we are thinking about the velocities. So this is going to give us information about where the velocity of the birds is going to point. So this can be shown as the result of very simple rules. The alignment of velocities, which means moving the same direction as your neighbors, attraction, remain close to your neighbors, and short range repulsion, that is avoid collisions. And by doing that, they produce amazing results. So these are very simple results. So one can see that without going into details, so we need to consider different parameters, but for high density and low noise, we see flocking behavior. And if we inform the model a little bit more, as I said, we will be able to make actual predictions. But still, there are many differences with respect to the Wicksec model and the Ising model. For instance, with respect to the control parameters. So this quantity here is analogous to the temperature, but we also have to include density, which is not part of the Ising model, because in the Ising model we represent particles by points, so density doesn't change. Whereas here, it's crucial. We assume self-propulsion, which is a property that has no analog in the Ising model. So this means that the birds put themselves in motion. Because of this, there is change of positions. There are less symmetries than in the Wicksec model. For instance, there is no conservation of momentum here. Actually, the flock works as a momentum sink, so the birds gain momentum, and this makes sense, right? And there is broken symmetry, but not an up-down symmetry as in the Ising model. It's a broken of a continuous symmetry because we assume that birds could point in any direction. Despite that, there are a lot of similarities, for instance, with respect to large-scale correlations in both cases, scale-free behavior, spontaneous symmetry breaking, and an important causal mechanism that is this cascading imitating mechanism, and locality. Locality seems to be crucial for the export of statistical mechanics to this type of case. What is important is that these similarities between the flocking behavior and the physical case are not only similarities with respect to the Ising model, but they are similarities with respect to all equilibrium models for ferromagnetism phase transition, or for paramagnetic ferromagnetic transition. So what I want to put forward is that this type of transfer that was very successful in the case of flocking doesn't correspond to any of the previous categories. It's not a case of imperialism, because we are not just expanding the model, the Ising model, to a new system. We are basically using the Ising model as an archetype to construct a very new model that has properties that are specific of flocks. It's not a case of model migration, because we are not just reinterpreting the variables and the idealization. We are adding new properties that have no analog in equilibrium thermodynamics, like self-propulsion. And it's not a case of templates, because it's not just the concepts, the general concepts and the formalisms that are exported from physics to biology, but also some causal mechanisms, like this tendency of individuals to imitate each other. So what I'm proposing that fits well with the case of the Wicksec model is a specific type of adaptation, in which the adapted model is created in the new field, that is biology, is constructed by borrowing certain properties of what I call the universal critical machinery. There are universal properties that are common to different models of equilibrium thermodynamics. And by also incorporating some domain-dependent properties, some of which having no analog in the original system. The properties that belong to the universal critical machinery are the ones that I mentioned before, including this cascading imitating mechanism and long-range correlations. And the properties that are domain-specific are self-propulsion, specific type of symmetries that are broken, specific control parameters, change of positions, etc. I don't know how much time do I? Wonderful. So then, I think this adaptation that is precisely this sort of intermediate approach that is not imperialism, and it's also not absolute skepticism, is the key of the success here of the Wicksec model. The Wicksec model is successful in the sense of being capable of making quantitative predictions and giving explanations, because it was successfully and adequately adapted to the new domain. If we would have had an imperialistic attitude with respect to flocks, we might have not succeeded in explaining the behavior of real flocks. So adaptation seems to be the key here. So while domain-dependent properties ground the applicability of the models to the new context and increase both the predictive and explanatory power of the model, the properties coming from the universal critical machinery increase mostly the explanatory power of the model. This is more content of how this looks in particular for this case. Now, last case about the claim of the application of statistical mechanics to economics. In In contrast to the VICSEC model, the application of statistical mechanics to financial markets hasn't been equally successful. It has led to some qualitative predictions, but unfortunately, we cannot use statistical mechanics yet to predict when the next crash will come. In contrast to Dougherty and Calendar, I will not say that this is because the project doesn't make sense to start with. I would say one of the reasons why this hasn't success, one of the reasons, or this is my guess, is because it hasn't been adapted enough. So what happens, I will not go into details of this, but one of them, there are different models that use statistical mechanics to explain the behavior of financial markets. One of the models that I have analyzed is the Johansen-Leroy-Sornet model that is based on the physics of criticality. So this model builds an analogy between magnetic materials, and in particular the transition from paramagnetism to ferromagnetism, and how the stock market behaves. So they replace the variables of the Ising model with the variables that make sense in the case of financial markets. For instance, they assume that, as in the case of magnetization of the Ising model, there are 2 degrees of freedom, up and down. They assume that in the case of the financial markets, the agents have 2 possibilities. They either buy or sell. Then they define the macroscopic, so the magnetization, that is the average state, in the same way. And they also define susceptibility in the same way. They move on to assume that the hazard rate, which is supposed to give us information about when the crash will occur, behaves in the same way as the magnetic susceptibility in magnetic materials, so as a power law. And then by using a little bit of calibration, they conclude that this exponent here for the case of the financial markets is a complex number, which gave rise to these log periodic oscillations here, which is basically where the predictive power of the model lies. So they said that these log periodic oscillations can be taken as the signal that the crash is coming. And then they contrast these log periodic oscillations with actual data, and they show that it fits with the data, even at the naked eye, right? So the model is not as bad as we might thought, even if it's very idealized. It has a moderate explanatory power in the sense that it tells us that a crash occurs very roughly and very generally as a consequence of a limitation between the traders that participate on the market. This is not a very full and complete explanation, but it gives us an idea of why markets might crash, right? And also has some predictive power in the sense of capability of making qualitative predictions. It tells us that if we see low periodic oscillations, that means that the crash might come. Right? Again, this doesn't allow us to predict when the crash will come. They are not quantitative, but they are qualitative. So they made some progress. So what I would say is that apart from the fact that the field might be complicated to model with statistical mechanics, one of the key problems of this model is that on the one hand, they incorporate certain universal properties from the physics of criticality that are the same as the VICSEC model. But in contrast to the VICSEC model, they don't use that much adaptation. So in fact, they don't define the microdynamics of the system. If we compare this model with other approaches to stock market crashes that define the microdynamics by taking into account the behavior of social agents, then we see some progress. For instance, Tayasu et al. Can actually give certain explanation of, for instance, intervention by the Bank of Japan in the financial market, which I found very interesting. So if we compare the JLS model with other more recent approaches that are more adapted also at the microscopic level because they are agent-based models, then we see some progress. So it seems to be that the problem with certain approaches of stock market of statistical mechanics applied to stock market crashes is not only that the field is difficult, but also that they haven't really adapted the model to the new field. I have said a lot already, so now let me conclude. So what I am defending here is that model adaptation, what I call model adaptation, is a special type of knowledge transfer that is different from imperialism, from migration, from templates, from skepticism, and from everything that has been proposed so far. And basically said that the model is adapted if it borrows certain formal and causal elements from the original domain, but also if it adds crucial properties of the intended domain. I argue that this schema can account for the predictive and explanatory power of the big set model and also explain to some extent the moderate failure of the JLS model in econophysics. My guess is that we could also use maybe an adaptation of the framework of adaptation to explain the transfer of statistical mechanics to other domains, even within physics, for instance, to self-gravitating systems and to black hole thermodynamics. However, although adaptation might work in all these cases, there are many domain-specific questions that one might have to answer. In the case of black hole thermodynamics, for instance, one would have to answer exactly which causal properties are transferred from the typical domain to black holes. And there is also the question that is different from the case of locking behavior about the validation of the transfer of statistical mechanics when empirical evidence is lacking. Some philosophers are proposing some ideas in this direction, but I would like to say more about that. Thank you.
Thank you so much. Thank you for the talk. I was wondering about adaptation or adaptationism in this context, which is a very nice balance between the extremism of imperialism and skepticism. But as thinking about this from foundational perspective and say the ontology of physical theories and the reduction of theories 1 to theory 2 to theory 3, I was wondering, is this compatible with reductionism, or does it suggest some kind of more autonomous high-level sciences, or maybe it's just completely neutral about the ontological reductions of various theories?
Yes, thank you. This is a very important question. I think there are different types of reductionism. And you realize that when you read Schrödinger. Then let me go back to Schrödinger, very inspirational book. So interestingly, the main claim of that book, What is Life, is that we cannot use statistical mechanics to understand the origin of life because statistical mechanics is incapable of explaining the phenomenon of dominance. So he basically said that we need to rely on the crystal, and that, according to the biologists, gave rise to the new program by Watson and Crick of that DNA molecule explaining inheritance. Right? Interestingly, in the biological community, Schrödinger's book is seen as the paradigm of reductionism because he's reducing all genetic information to DNA. But for us as philosophers of physics interested in reduction, this is the most anti-reductionist book because he's saying, well, you cannot reduce either to statistical mechanics or to quantum mechanics. So I think it all depends on the type of reduction that we are considering. So I'm very sympathetic to this, at least ontologically, to this idea that everything is constituted by the most fundamental entities of physics, whatever they are. But this doesn't mean that when we work at a transversal level, so when we compare different domains, we can just reduce in the sense of dominate one discipline by another without taking into account certain difference. So it allows for the autonomy of the new field, but it's compatible in principle with a more reductionist ontological picture, which is something that I am sympathetic about.
Okay, thank you so much.
Oh, thank you. Well, that was a beautiful talk, and I had many things I wanted to ask or comment on. But starting from your question about reductionism, there was some distinction famously made by Einstein in his paper where he first described relativity for the London Times, between theories of construction and theories of principle. And he said, of course, that special relativity, like thermodynamics, is a theory of principle, which means that you just start out from these empirical principles, as he called them, rough and general and crude generalizations that seem almost obviously necessarily true. I'm not saying that Einstein said that, but that's roughly my description of them. And he contrasted them to theories of construction, which start from clear ontological simple systems and try to construct more complex systems out of those. Now, thermodynamics is a main and paradigmatic example of a theory of principle, because it just focuses on a few macroscopic observable quantities and ignores all the macroscopic detail. Microscope, yeah, that's what I meant to say. I would argue that statistical mechanics, certainly in the hands of Gibbs, is also a theory of principle. Because what Gibbs does is really just focus on a Hamiltonian system. So there's a sense of energy, there are evolution equations, and he constructs all these analogies with thermodynamics. But the idea that the system consists of molecules only enters in the very, very last chapter of his book. The rest is completely independent of whether we talk about a system consisting of molecules. So it's because of this very general framework, I think that this is also a theory of principle. This is actually quite in contrast with Boltzmann, for whom the fact that the system consists of molecules that can collide is at the very heart of all his ideas. And it's precisely because Gibbs's approach to statistical mechanics is so general, is a theory of principle, that it can be exported to many other domains in a successful way. And so I also, and also it means that these exportations are not necessarily reductions.
Yes.
And I wanted also to add one other remark that I had, and this is just to expand your stock of examples, I think. You talked about the Ising model and application of statistical mechanics to magnets, which is a late 19th century idea. But in a sense, this also introduces very important disanalogies, which were not present in Boltzmann's approach, for example. And one of them, the main, I mean, it's not very controversial anymore, but one of the ideas is that absolute temperatures can become negative because the phase space is no longer a Cartesian product of space and momentum coordinates. And as a result, there is a maximum as well as a minimal energy state. And that implies that there could also be negative absolute temperatures. You cannot always pump more energy into your system as you could for a system consisting of moving molecules. And this was at the time when people started to realize that you could have negative absolute temperatures. This was something of a conceptual reset, because in ordinary thermodynamics and kinetic theory, it seems to be almost folklore wisdom that temperature is the mean kinetic energy of the molecules. That this was the definition of temperature. And this, of course, is no longer true if absolute temperatures become negative. So there are also important disanalogies even in that extension. And very often, I mean, what we call theories are very often just conglomerates of different sets of approaches with some common elements. But what we now call statistical mechanics no longer is just restricted to the ideas of systems consisting of molecules in motion. And that by itself is maybe an imperialist strategy, but it means that there is a complex mechanism of extension and adaptation involved in all this.
Yeah, so I think I will just briefly, very interesting. So I will briefly go back. So this is actually what you said about Gibbs. It's right, and this is normally the justification that people find to use the Gibbsian approach and statistical mechanics in general everywhere, because they assume that if we focus on the macroscopic behavior and not on the molecules, etc., then we will find the same type of behavior in very different systems, so very close to multiple realizability. And this has been used as a justification also for a more imperialistic attitude of the framework, because it is assumed that at the macroscopic level, we have the same behavior. What I'm saying is that if we have that view, we might not go very far in the application of statistical mechanics to very different domains, including biological processes and socioeconomic systems. In fact, it seems that the only way the field has made progress, in contrast to the original idea of self-organized criticality that was very imperialistic and didn't go that far, is that they are calibrating not only the microscopic level, but also the macroscopic level to make it applicable to different domains. So basically, this is exactly the aspect in which this idea that sounds very, very trivial, it's not, because it really changed the way of using statistical mechanics to different domains. But that's a very important point. And the other of the negative, yeah, in long-range interactive system, there's also negative specific here. So you find these analogies, negative absolute temperature.
And that's partly because so many people, when they talk about thermodynamics, they often just think of the ideal gas.
Yes.
As the only prime example of thermodynamics. They misrepresent or they underestimate the power of that theory to describe other systems.
Yes, but what I would stress is that if I am right, if that the power doesn't come from a straightforward application of statistical mechanics everywhere, like the laws of Newton that can be applied universally, but it comes a lot from adapting to different domains.
Eugene had his hand up online. You want to go to the next? Oh, sure.
Hi, can you hear me? Hello?
Yeah.
Okay, perfect. Thanks for the wonderful talk. I think I'm pretty much in line with your idea of adaptation. If I understand it correctly, like adaptation in the sense that bring the kind of causal aspect and formal aspect of the more universal model, and then add some context-specific elements in the modeling. I think that's helpful, especially I think the actual advantage could be that, well, it helps to reduce the possibility of like proponents of the universality explanation to introduce essential idealizations in like modeling different things. I like that. But let me ask first a clarificatory question. When you say there are different types of black holes from stable to quasi-stable to non-stable, I take it that you don't mean like a stationary black hole under different types of perturbation, like under mild or more turbulent perturbations. Can you explain a little bit more on that? And also the related question is, if some of them are theoretical constructs, and how well we know about them and how physically they are. That's the first question.
Yeah, the second I didn't get it. Can you repeat the second?
Oh, sorry, I didn't say the second question yet.
Okay, but the second part of the first question.
Oh, the second part is so first I will beg you to explain a little bit what do you mean by different types of black holes, and then if they don't mean that there are different stages of a like black holes that will kind of ultimately go to stationary state, then what will those black holes be, and how well do we know about them, like physically and theoretically?
Yeah, so about type of black holes, I'm thinking about stationary versus rotational, for instance. So I'm thinking about different type of idealizing assumptions that you might consider to study the physics of the black hole. So if we assume that the black hole is stationary, then we will have certain type of assumptions that derive from that. If it's rotational, for instance, we will have other type of assumptions. If it's eternal, for instance, or if it started from the collapse, right? So you are going to see also some physical differences. So I'm thinking about different idealizing assumptions that you might take to understand or to model the black hole.
I see. But like, but those black holes, then let me say, like those ordinary black holes that we can observe in principle in the universe, although they like undergo different stages, different perturbations, or they have different like different like physical configurations, like rotation or just being massive without rotation, but they can all go ultimately like for a long time to stationary states. So we can still say that most of them are just stable black holes, right? Okay, thanks. I mean, I thought you might mean something like the primordial black holes, etc. But okay, sorry, that's the first question. And the second question is, I want to say something more broad. Namely, I want to support your argument by saying that, well, even within the physics context, I think the universality kind of break down in the black hole case, because in the black hole case, I think there are different senses of universalities. So for example, as you mentioned, we have the universality of Hawking radiation, and you have a nice paper with Shom and Karim on it, in which you argue that, well, the Wilsonian renormalization group method doesn't really do well in that context, right? And also we have the universality of black hole in the sense of Choptuic simulation work, in which you study, he studied the possible universality class of initial data that could later lead to formation of black holes, right? And in that context, I don't see a yet successful way of putting forward the renormalization group method in that context. And then the most important universality sense is the universality of different stationary black holes as formed by possibly many different collapsing matters or procedures, right? And in that case, I also don't see a successful renormalization group method yet. Maybe I'm wrong, but let me know. If that's the case, I think even in the physics to physics context, it's not completely warranted to just borrow the universality to adapt to the other cases.
Yeah, I agree. I have that paper with Karim and Shan on universality of black holes, but I still think maybe not in the same sense as Wilson, but we might be able to distinguish between different types of black holes, and in a way of understanding when does it make sense, or when is it more straightforward to apply statistical mechanism, when it's not. So I'm thinking about universality classes in a more relaxed way than in the Wilsonian case. So I'm not committing that you apply renormalization group methods. I'm thinking about being able to classify different types of black holes, some of which will be more susceptible of statistical mechanics than others. But this is just what my guess. So I have research to do there.
Yeah, Thanks. That's super helpful.
Thank you. This is very interesting, and I very much like this picture that you've got here of a universal machinery applied in specific, adapted to certain kinds of cases. One question about the V-check model is there some kind of size? Is a prediction of the model you get very qualitatively different behavior depending on the size of the flock? Just my own experience of watching flocks of starlings. In Europe, you have much larger flocks of starlings and much more spectacular murmurations than we do in North America. And is that the sort of thing that you get as a prediction of the model?
Yes, absolutely.
Yeah.
So this is the reason why the biggest project of flocking behavior are in Rome.
Right.
Absolutely. They have millions, and it's not 100. There are millions of birds who flock. Which flock?
Yeah, like in North America, we're lucky to get flocks of hundreds.
It changes the behavior, for instance. Well, this is details on flocking. I don't know if you're interested, but before when Vixek proposed the model and they started working with simulations, they thought it would be just two phases: the disorder phase, in which just birds wander around, and the order phase in which they flock nicely. But they had to run simulations with more than millions of birds to understand that there was a third phase, which was observed actually in Rome, in which they cluster. So it's not only from disorder to order, but if you get higher flocks, or so bigger flocks, you're going to get also different type of behavior. So there is this cluster, which is very close to this reinforcing dynamics or clustering, close to echo chambers. So this is why also some people working on social sciences are using that as a prototype to model echo chambers, because they start building this cluster. So
okay, cool. You made me want to learn more about this. Is there anyone else in the queue? I actually have another. Yeah, okay, I'll come back if there's time.
Yeah, no, I just thank you for the talk. It was very clear and enjoyable. I wonder, so you discussed the application of thermodynamics to black holes, cluster galaxies, etc., and the adaptation needed. I was surprised that you did not mention. I mean, I wonder if you think that there is something like an imperialistic attitude in the application of thermodynamics to statistical mechanical systems, whether you think that there were needed some like adaptation or it was just straightforward. So
yeah, so well, on top of my head, the idea that you could recover the exact law of thermodynamics, that was the first project, one of the first projects of Boltzmann. They wanted to recover the deterministic character of the second law, and they thought, well, here Josh Kekor knows better about the history of statistical mechanics, but they thought that it was a problem for statistical mechanics that they weren't able to actually recover the exact second law, the exact laws of thermodynamics. So this is an instance in which adaptation was required and actually made the field improve, because we believe now that the statistical version of the second law is much more accurate than thermodynamics. Right?
yeah. Okay, thank you.
Thanks. I wanted to, this is going to overlap with Jos a little bit, say something in favor of the sort of imperialistic attitude to galactic dynamics. I mean, here's the way of putting it in an imperialistic way. I'm interested in studying a very large class of systems that can be well modeled as point particles, as large swarms of point particles interacting by some two-body force. And then from that point of view, the only fundamental difference between gases and star clusters is the particular force, and likewise plasmas or something. And then I could say, okay, firstly, can I get away with treating that system statistically? In other words, like, do I need to keep track of the individual points, or can I do some kind of statistical or probabilistic average over them? And then, if we care what happens to Earth, then I suppose we can't do it. But if we're interested in this stuff in the bulk, that method looks fine all across the story. And then we want to say, okay, well, can we derive dynamical equations for that? And then there's a bunch of moves, but to pick one, I can do BBGKY. And again, the formal technology looks good in all of those situations. As always in physics, the approximation schemes I use in different places look different. So in gases with short-range interactions, I can ignore the mean body aspects of it. In some galactic contexts, I can ignore the collisional term and just get a Vlasov term. In some plasma cases, I can do that. In some plasma cases and galaxy cases, I can't. Okay, then I can ask, does the system reach local thermal equilibrium? Does the distribution locally relax to something like the Boltzmann distribution? And I can say yes for short-range gases. Yes, sometimes for galaxies or for stellar systems. So kind of yes in globular clusters, no in galaxies. And if it does relax to local equilibrium, can I say, does it evolve to global equilibrium? Then I can say yes in short-range force frameworks, yes in plasmas, no, definitely no in galactic dynamics. And if it does relax to equilibrium, can I do thermodynamics on it? And that feels like a fairly systematic kind of checklist to work through if you're doing the statistical mechanics of that whole class of systems. And then I'm not really seeing a fundamental difference between how that plays out in the galactic dynamics, what the technique is in the galactic dynamics case as compared to the dilute gas case. The actual answers are different. Of course, it's a different force interaction, and it turns out that universal long-range, universally attractive forces give you extremely different qualitative behavior than repulsive short distance forces and also than electrostatic long range forces. That's great. That's good physics. And it turns out these systems are much harder to study than dilute gases. But, again, that's life. Crystal systems of defect are hard to study as well. That's how it goes. I mean, it feels like that's a paradigmatic example of just applying the power and technology of statistical mechanics to this particular system just with a new potential. So why shouldn't I think of that as imperialism? Why do I have to think of this in this adaptation way? I mean, maybe the answer is just I misunderstand what you mean by adaptation, but perhaps if you could just say what you think there.
Yes, so thank you. I agree that maybe it makes sense that the default position is this imperialistic attitude because you want to simplify your life, right? So saying like if we have already a theory that is developed enough in which we have proved some theorems, we have different approaches to thermodynamics, right? We have figured many things out in many years, so it makes sense to try to use the same framework to different domains. So so imperialism as a default position, I think makes sense. Even maybe if you try to expand it to economics as a sort of in the explanatory phase, let's say. So what I would say, but again, especially in the case of long-range interacting systems and black holes, so these are my preliminary ideas. Now I want to do like a detailed research on that. But what I would say is that you should push that forward as long as you can. But there is a point in which if you start seeing that many crucial concepts like entropy, equilibrium, some key concepts of thermodynamics, the ensemble, so if you have to replace Boltzmann-Maxwell equilibrium for something like metastable equilibrium, if in order to make that physically plausible, you have to redefine that equilibrium, like in the sense of Lindenbelt or Tzali. So if you end up, in order to find results that are empirically adequate or that are measured with some other degree of success, other kind of success, if in order to achieve that, you need to modify crucial parts. There is a point in which the horse is not the horse anymore, and you have to admit, okay, it is a cat, or it's sort of a unicorn, right? Something different, so related but not the same. So I would say, I understand the imperialistic attitude not as a very bad attitude in general. So I think Newton was successful in classical quantum mechanics as well, many different fields, so including thermodynamics as well. So I don't think that it should only be restricted to the specific domain that was the original domain in the 19th century. I think imperialism is a good thing in this very specific sense. But there is a point in which one starts seeing these differences, and I'm seeing these differences in black hole thermodynamics, for instance, also with this idea of galaxies, right? That many crucial aspects of statistical mechanics are being changed. So I would say there is a point in which we might have to admit, well, actually adaptation is what is happening here and not really just the extension of the previous domain to the new domain.
Yeah, maybe it's just terminological, but I mean, it feels as if, the claim that systems equilibrate is not supposed to be an a priori presupposition. It's a dynamical claim that's how systems evolve. And if some systems don't equilibrate, terrific. And if they don't equilibrate, we can't do equilibrium dynamic on them. So, I mean, one thing you might say, look, it might have been reasonable. I'm not even convinced this is true, but it might have been reasonable to hypothesize that galaxies are at thermal equilibrium. And then you look and they're clearly not.
Yes.
But that didn't in any way obviate the application of statistical mechanical technology to them. It just turns out they don't equilibrate. I mean, there might be other systems where you can't apply the technology, but I want to distinguish between applying the technology and finding a way to a novel location versus the technology just not being applicable.
Yeah, but here I would, and this is the last thing that I say on this, because as I said, this is a research that I want to do in the next years of my life. But there, I do have something to say on that. So one idea is to say, well, they will eventually evolve to Maxwell-Boltzmann equilibrium. They seem to be evolving towards that.
They won't. The gravithermal catastrophe. They
won't.
They definitely won't. That's a theorem.
But they might stay outside of equilibrium forever, which is okay, because it might be consistent with a statistical mechanical framework. But another option, which was, as far as I understand, what Lindenfeld and Salis had in mind, is that we might try to find a way of defining equilibrium differently in this case. And this is also one of the motivations to find a different expression for entropy, that is the Salis entropy or the Lindenfeld entropy, that we don't need if we are studying gases. Maybe there's a way of making sense of that for a certain time scale, but normally we don't need it. We assume, okay, they will equilibrate, that's all fine. But in this case, they are actually trying to redefine equilibrium. So this is more or less what I had in mind. We can say, okay, they don't equilibrate, they stay out of equilibrium forever, but we might take a different approach and say, well, there are reasons to consider them in equilibrium. It's just not Boltzmann-Maxwell equilibrium. And for that, we would have to do more empirical research to see what kind of distribution, what kind of equilibrium makes sense for that case. But there's much more to investigate.
I should ask you.
Thanks very much. Super interesting. I think a way to put my question would be, at one point you differentiated between a couple classes of views. You said that according to like universality and imperialistic approaches, black holes are thermodynamic systems, quote, in the fullest sense of the term. And then the contrast view was something like they're merely formal analogies. And I think my question is basically, what is that distinction exactly? Sort of following up on what David was saying, I'm thinking you're totally welcome to borrow any formal technology from any domain of wherever and apply it and see if it gives you some sort of workable result in any other domain. I'm thinking, none of these systems have the same sort of basic ontology that they're positing, the birds, so how are we distinct, like what's meant by like fullest sense as opposed to just like there's so one person could say something like, well, there's just some like subclass of techniques from mathematical techniques, formal techniques from this one area that are very well applied to this other area. And then it's a little bit of a kind of like semantic decision whether we call that thermodynamics, but that's all there is. Like, is there something more philosophically interesting than that?
Yeah, so basically what Walt suggests, but he's not the only one. So there's this tendency to think that all the work done in black hole thermodynamics that has actually given a lot of results in the last years lead us to assume that basically the same thermodynamic principles that govern, well, the coffee in your glass or in your cup are the ones governing black holes. So there's this idea that or at least implicit, that black hole thermodynamics is just the extension of thermodynamics. And this is what I call the imperialistic attitude. Now, the other position that you find is, for instance, again, they are not the only ones, but represented because they are very critical in that paper, Calendar and Dougherty. They said, well, this is just no more than formal analogies, and then they sort of are dismissive with the use of statistical mechanics in economics, and that's it. So it seems that we have these two options. What I'm proposing is something in between. But then to make it more interesting, I would have to say, well, exactly which properties are transferred, and there's much more research to be done yet. But my intuition is that it's not just the application or the extension of statistical mechanics. There's something different and more interesting going on in black holes. And this is perhaps also the reason why you have black hole entropy, black hole temperatures. It's not like using classical mechanics to understand the behavior of the moon and the Earth, which are basically the same. Here, there seems to be something more interesting going on. And my argument is that if we look at what happens with flocking behavior, which is my example of a very successful application of statistical mechanics, then you see that the key is not just to use what is said, the Ising model, to understand birds. If you do that, you're not going very far. Because if you get rid of self-propulsion and the active motion, you cannot explain even why birds flock. But it's also not just a formal analogy. I said there is something more interesting. You might even say that there is something physical in common between magnets exhibiting a phase transition from paramagnetism to ferromagnetism and flux, going from a disordered phase to an ordered phase. So it's not just a formal analogy there either. So I would say in the case of biology, we find something in between. So my intuition is that that will also make sense in other parts within physics. But in order to say more, I need to do more.
Thanks.